Our next speaker is Mark Spradlin from Brown, and he'll tell us about symbol alphabets from positive geometries.
Okay, thanks for the invitation to speak. It's really an honor because most of the credit for this work that I'll be talking about goes to my exceptional collaborators who are listed here. In fact, the last 5 of these have been volunteered to participate in the discussion session that will follow my talk. Jorge Mago is an exceptional student we have at Brown who will probably be graduating next year. Oh, sorry, not the last 5, these 5, 1, 2, 3, 4, 5. And Jorge will probably be graduating. And this guy Nima also shows really a lot of promise. So yeah. So I'm going to be reviewing a body of work, and the fact that I'll be reviewing a lot of things means that it's almost guaranteed that every individual slide that I show will be boring to someone in the audience, but hopefully for every individual person, there will be at least one slide that's non-boring. So that will be my modest goal today. Okay, so just by way of introduction, why are we all here? We're here because the scattering amplitudes of planar n equals 4 super-Yang Mills theory constitute a remarkable collection of functions with apparent but still far from understood connections to many interesting areas of mathematics. And there's a vast array of such functions. So for those of you who are coming to this field, maybe as somewhat partially being outsiders, it can be quite overwhelming because there's a whole universe of different kinds of things we talk about, from rational functions to differential forms on positive geometries to integrals over Calabi-Yau moduli spaces. And all of these are interrelated with each other and fall under the general scheme of amplitudes. So I'll try to be a little more precise about which aspect I'm talking about when the time comes. And specifically, I'll be reviewing what we know about symbol alphabets of these amplitudes and describe some approaches that hope to explain them using various mathematical constructions. Oh, and here I mention again that the discussion session following my talk will feature several examples worked out in great detail by my collaborators. Okay, so there's no better way to get started than to stare at an example. The definitions, well, some of the definitions will follow, but just to get a flavor for what's going on, let's look at an example here. So this is a formula for the 2-loop 6-point MHV amplitude. And in order to try to connect with all the various parameters that some of you have seen, that show up in various talks. This is m equals 4, l equals 2, n equals 6, and k equals 0. It's a function that looks like the following form. In a research article, you can fit it on one line. It doesn't conveniently fit on one line of a slide because you have to define a lot of auxiliary things. But the most important aspects of this function are still accurately represented here on the slide. It's a polylogarithmic function involving this function Lie that many of you are presumably familiar with. Plus, so there are 2 terms that I've written here. There are additional terms that are equal to products of similar functions of lower weight. And then there's an additional sum of the whole thing over the Z6 cyclic symmetry that cyclically rotates all of these labels. Now these brackets here are Plücker coordinates on the Grassmannian G4, 6. So if you imagine a 6x4 matrix of momentum twisters, then IJKL is just the determinant of the columns I, J, K, and L. Now, this formula has many remarkable features, not all of which are apparent. Some you have to actually start calculating and witness some magic happening. But one of the things that is apparent just by looking at it, the way I've presented it here, is the appearance of these Plücker coordinates. And the fact that the set of Plücker coordinates for G4, 6 is equal to the set of cluster variables for G4, 6. Now, this is just an accident for G46. It's certainly not true for general Grassmannian cluster algebras. But in these papers, it's in particular in the second paper, a lot of examples were looked at for n equals 7 and also for higher n at 2 loops. And these cluster variables of the Grassmannian cluster algebra G4 comma n started to appear ubiquitously in these kinds of expressions. So I want to, in my next slide, this was just to give you an impression of the kind of thing we're looking at. And in my next slide, I want to be a little bit more precise about what I mean by this word, whether something appears in a formula, because you might think, well, I can rewrite the formula in a different way to make something else appear, to make something that doesn't appear, or to make something that does appear, disappear. So what do I mean by that word? In order to explain what I mean by that word, I need to review the definition of the symbol of a transcendental function. Now, in physics papers, we often omit this first step, but this is actually the crucial step. We need to fix some base field of functions. Basically, we're going to define the weight of a polylogarithmic function recursively, and we need to start by defining what we mean by a function of weight 1. And a function of weight 1 is a logarithm of some element of our function field f. Okay, so in our applications to scattering amplitudes, f will be the field of homogeneous algebraic functions of Plicker coordinates on Gm comma n. And once you start with that, then a function of weight k, a transcendental function of weight k, is one that has the property that this differential equation holds. So what it means is that there's a collection of r's and functions fi of lower transcendental weight, such that the differential of f of k can be written as this linear combination. Okay, now this is not a unique, this formula is not unique because if you have a product of two things inside this logarithm, you could split it up. If you have a ratio, d log of a over b is d log a minus d log b. So you can do some reshuffling here, but the statement is just that if such a representation exists, then we say that f has weight k. And I should have said, ultimately we need to seed this by functions of weight 0, which we will just take to be rational numbers. Okay, so this is a recursive definition, which means that once you've sort of broken down a weight k function into these weight k minus 1 functions, you can continue iterating and break each of these weight k minus 1 functions down into weight k minus 2 functions, etc. Okay, so a symbol alphabet of a transcendental function fk is a basis for the vector space spanned by the finite. So we always assume these are finite sums. That's part of the definition of being a transcendental function. The finite collection of all the logarithms of these factors that appear as you break down the function into its atoms. So you can, if you think about the function f as like a molecule, then you're breaking it down into these individual atoms. And an element of this vector space is called a symbol letter. Okay, so just by way of some simple examples, if you have the function log of z to the power n, it has a single symbol letter, z. Oops, got my eraser going there. Well, you could also choose 1 over z as your symbol letter, or 1 over z to the 5th, because the logarithm of all of those spans the same space, right? The logarithm of 1 over z to the 5th is -5 times the logarithm of z. So it spans, the rational linear combinations of -5 log z is the same vector space as rational linear combinations of log z. For a slightly more non-trivial example of that simple fact, if we look at the polylogarithm function Lie k of z for k greater than 1, this has a symbol alphabet that's usually taken to be 1 minus z comma z. And here, by convention, we always omit writing the word log just to save ink. But in our heads, you should always remember that the logarithm is really there. And so when you see this, you're really thinking of the functions log 1 minus z and log z, because you could choose a different basis for the symbol alphabet. If you were so motivated, you could choose this basis for your symbol alphabet, because rational linear combinations of the logarithms of these give you the same vector space as rational linear combinations of the logarithms of these. So it's acceptable to say that the symbol alphabet is this. It's also acceptable to say that the symbol alphabet is this. Okay, and please don't hesitate to interrupt me if there are any questions whatsoever. Yeah, I hope that much of what I'm saying is well known to many people in the audience, but I don't want to leave anyone behind. So let me review what's known. Previously, I gave an example, a particular example. Really, the one nice thing about this example that I gave earlier is that it's really the only non-trivial multi-loop amplitude whose essential qualities you can write on a slide. Okay, very quickly you have to start emailing Mathematica files back and forth with your collaborators in order to really provide all the content of these amplitudes. But I can summarize what's known about their symbol alphabets on this slide. So first of all, for the m equals 4, which is the real n equals 4 super Yang-Mills theory, in this case, amplitudes with n less than 6 particles are in a sense trivial. I won't say more about what I mean by that, but they're sort of completely determined up to infrared divergences. It's believed, well, I'll say more about this later, but all currently known symbol letters of 6 particle amplitudes are given by the Plücker coordinates of G46, which is in precise correspondence with the cluster variables, and a symbol alphabet for all 7 particle amplitudes, right? So here, if I hadn't already shown you this slide, and you were anticipating which direction I would go in, you could ask, well, is the generalization going to be this, or is the generalization going to be this? Because they no longer agree starting at n equals 7. And the answer, because I've already displayed my slide, the answer is that the correct generalization seems to be, at least as far as we know in all known examples, that the symbol letters are given by the G47 cluster variables, which include the G47 Plücker coordinates together with 14 other rather innocent looking homogeneous polynomials in Plücker coordinates. I've written two representative of each of the cyclic classes here. And it is expected that these facts here continue to hold for all 6 and 7 particle amplitudes for any k, that is any MHV degree, and any loop order L. Whereas for n equals 7, for n greater than 7, there are several interesting new features and puzzles that will be one of the main themes of my talk. Okay. So what are these new features? Well, first of all, if you're a cluster algebraist, you know that the Grassmannian cluster algebra G4n for n greater than 7 becomes infinite, meaning there are infinitely many cluster variables. Yet from physical grounds, we expect that for any finite n, it's not quite say, we can't really say this is proven, not even at the level of a physicist's proof, maybe we can discuss this more in the discussion, but it's expected that for any finite n, but arbitrary k and l, there are only finitely many symbol letters that should appear, with some caveats that I might get to in a later slide. In addition, well, okay, this is based on expectations and guesses, but one thing we know for sure is that for n greater than 7, you begin to see symbol letters that are non-trivial algebraic functions of the Plöcker coordinates. So let me give you a prime example that will recur throughout my talk and in the discussion session afterwards. For n equals 8, there's a symbol letter that physicists know of as being, we call it 4-mass box type. But if you want to write a specific formula for it, here's one way to write it. Remember, there's always some multiplicative ambiguity in choosing a basis for a symbol alphabet, but here's a convenient way of writing a symbol letter. In terms of quantities A and B, we're going to see these A's and B's also a lot. So there are many interesting features about this formula. One thing that I'm going to talk a lot about later is the fact that this 4 here is really a critical number. So if you look at this quantity B, it's obviously positively valued everywhere inside the positive Grassmannian. So if all the Plöcker coordinates take positive values, then this B is obviously a positive real number. What's less obvious, you can't really tell just by looking at it, although it's relatively simple to prove. This A quantity is also positive value, notwithstanding these minus signs. Okay, so everywhere inside the positive Grassmannian, this term dominates over the sum of these two terms so that A is positive. In fact, A is what we call over positive. It's too positive, meaning that you can subtract things. Well, what it specifically means, I'm not giving the definition we give in the paper because this is all still part of my introduction and motivation. But what it means in practice is, for example, if you look at this quantity a squared minus 4b, here you have the quantity a that's positive, and you're subtracting from it something that's positive. So it turns out that this thing is still positive valued inside the positive Grassmannian, but barely so. So this number 4 is critical. If you try to subtract, if you put a number bigger than 4 here, then this thing would dip negative. There would be some place inside the positive Grassmannian where this would dip negative. Whereas if you put a number less than 4 here, then you haven't subtracted enough. You know, there would be, you could subtract a tiny bit more and still keep it positive. So anyway, as a consequence, this square root is real valued everywhere inside the positive domain. And this ratio takes values between 0 and 1 inside the positive domain, inside the positive Grassmannian G48. Okay, another feature that appears for higher values of n, and I'll have very little to say about this, is that we know that most amplitudes, in some sense a set of measure 0, most amplitudes are not in the class of transcendental functions that I described above. They have more complicated analytic structure. So everything I say today about symbol alphabets will not directly be applicable to those amplitudes. But some of the philosophy that I'll talk about in a few minutes, having to do with branch cut structure on boundaries of positive domains, some of that philosophy should still translate to these more complicated amplitudes, but in a way that we currently really have no idea how it works. Okay, so let me summarize here what's currently known about the symbol alphabets of amplitudes in n=4 Yang-Mills theory. So here I've sorted the columns by n, the number of particles, and then the rows separate the number of rational letters. In fact, you can always choose them to be homogeneous polynomials in Plücker coordinates, but we use the word rational because of this ambiguity. You can always divide and multiply things. So you can choose them to be rational, but in particular, you can choose them to be polynomial. These are the 15 Plücker coordinates of G46. These are the 49 cluster variables of G47. I'm including here the frozen variables. There are currently 180 known, you can open the literature and find calculations and look up a list of 180 symbol letters that appear in 8 particle amplitudes and 531 that appear in 9 particle amplitudes, as far as have currently been computed. The question marks indicate that future computations may well increase these numbers. Now, as far as the algebraic letters, we see 18 of them at n=8, and so far 99 of them at n=9. Now, the whole goal of this research program is to seek some kind of mathematics that will help us understand these things and maybe explain or predict them. And there are 2 motivations for that. One is sort of just like we want to understand the mathematical structure, and there's some deep mathematics here, and it's beautiful, and these amplitudes are amazing, and they should reflect something remarkable. There's also a more practical pedestrian approach, which is that if we had some way to determine what these things are, it would really, really help us calculate new amplitudes. So in that vein, I have here sort of like a hall of fame here, because many thanks go to the enormous number of people who have done the hard work of collecting all this data over years of non-trivial calculations. And I've lumped them all together. Well, hopefully most of them. Sorry if I've forgotten you. I've lumped many of them together here, beginning with work in the 90s, calculating the one-loop amplitudes by people like Byrne, Dixon, Dunbar, and Kosover. And then there was a seminal paper by Caron-Huot calculating the 2-loop MHV amplitudes using a Q-bar equation that recently has been put to tremendous use by Song He and his collaborators, especially insofar as collecting some of this information. So these are like the heroes here, the astronomers who are carefully and very precisely measuring the positions of the planets. And compared to these hardworking individuals, I'm like the semi-crazed astrologer running around trying to see if I can see the face of God in these numbers. Okay, so that's sort of the philosophy here. Okay. Now, since this is a conference on positive geometry, I want to say at least a few words. I already touched on this subject briefly, but I should say a few words about where the positive geometry is or might be. Okay, so back to this example that I've looked at. Of course, this is a multi-valued function on a space we call configuration space of 6 points in P3, or more generally, conf k comma n is the configuration space of n points in Pk minus 1. And for generic points, you can represent this as an element of the Grassmannian Gk comma n modulo the torus action that individually rescales each column. If you have a k by n matrix that represents a point in GKN, and you consider the torus action that rescales each of the columns, because the columns represent homogeneous coordinates of a point in Pk minus 1, then this quotient space for generic points in the quotient space is that configuration space. And the tilde here Gontchoff originally long ago told us to put the tilde there because this represents a birational isomorphism, meaning that you have to be, for the physicists in the audience, what that means is you have to be super careful about what happens at exceptional configurations. Of course, that's where all the interesting stuff happens. Because this function has branch point singularities on the boundary of, but nowhere inside the positive domain. Okay, I've already referred to this obliquely. This is the image in this quotient space of the totally positive Grassmannian. That is the Grassmannian where all Hooker coordinates are positive. Now, a central conjecture of our field is that for all amplitudes, that means for any n, k, and l, even including those beyond transcendental type, are non-singular everywhere inside this positive domain. Okay. So we are, as I already alluded to, we are extremely interested precisely in what happens on the boundary for two reasons. Well, in physics, it's been a long-standing goal, I guess going back to Dirac probably, that there should be a method to determine amplitudes based on general constraints on their analytic structure. And mathematically, we're interested in the boundary structure in part because the totally positive Grassmannian is by itself is not a positive geometry. It's homeomorphic to a ball. And it's not a positive geometry until you specify what you want to do with its boundary, specifically how you want to compactify its boundary. Now, there's no intrinsic answer to the question, what does the boundary look like? The answer to that question, as we all know here at this conference, is that it depends on the class of functions under consideration. So just to pick one very well-known example, you can parameterize the totally positive configuration space 2, 5 by a matrix representative of this form, where the two parameters, z1 and z2, are real numbers that take values in this range, 0 less than z1, less than z2, less than 1. And if you just saw this, you would say, aha, the space you're talking about is a triangle, okay? It has 3 boundaries. But we know that if you look at more complicated functions, specifically cross ratios of this type, where these brackets are the Plücker coordinates and all indices are understood mod 5, then 5 boundaries become apparent, not just 3. So I took this figure from this paper. It's also drawn many other places. So what looks like a triangle maps out into this more complicated sort of surface that has sort of 5 boundary segments manifest. So these are two different, as positive geometries, these are definitely different from each other. They have different boundaries, but their interiors are essentially identical. They're homeomorphic to each other. Okay, so the question is, what, if anything, is or are the positive geometries that we should associate to loop amplitudes of the type that I've been discussing? Well, before I get to that, just to connect with other talks at this conference, we know that at tree level, the positive geometry underlying the n, k, m amplitude is the amplituhedron. I should have a citation here to Arkani, Hamed, and Trinka. Oops. And that furthermore, the unique canonical form associated to that amplitude, to that geometry, is the tree level amplitude. Now at loop level, we still don't fully know which positive geometries are relevant, and the rule for associating transcendental or worse functions to these geometries is even less clear. So here we know what the geometry is, and we know what the rule is for assigning an amplitude function to that geometry. When we go to loop level, we're still at the stage of exploring possible candidate positive geometries, and we're not yet even at the stage, except for draft notes that have been sent around by various people, we're not yet even at the stage of trying, I'm sorry, well, with one big exception. The big exception is we know how to associate these string integral type functions to positive geometries based on the work of Songhi, Thomas Lamb, and Nimar Khani Hamed, but we don't yet have a mechanism to naturally associate the polylogarithmic type functions that we're looking for the amplitudes of n equals 4 super Yang-Mills theory. So our philosophy is to explore various candidate positive geometries whose structure might imprint on amplitudes in a way that we can decipher. Okay, so I'm pretty much exactly on time because I'm 31 minutes after I started, and I finished my philosophy / introduction / motivation section. Because in the rest of my talk, I want to describe two constructions for partly explaining the data regarding the symbol letters of amplitudes in n equals 4 Yang-Mills theory. So let me stop now to catch my breath. So part one has to do with an approach that involves recognizing, deriving is somewhat too strong of a word, as you'll see in a moment, but recognizing that symbol letters naturally, for reasons we don't fully understand, seem to emerge from a very simple process that involves solving a matrix equation. Okay, and this is based on work on in collaboration with these people, and also there was a simultaneous paper by Songhi and Lee. So this is an extremely simple matrix equation. C and Z are matrices that I'll define in the next slide. And these kinds of equations for physicists, they date back all the way to the beginning of the Grassmannian formulation of scattering amplitudes, 12 years ago. So I'm not going to review the entire history of the physics behind this. Let's just see how this works. Okay, so if you're a mathematician and you haven't followed anything what I've said yet, you can hopefully tune in again, and maybe this is semi-self-contained now. So we're going to let Z be an n by m matrix. We call it the momentum twister matrix, representing the homogeneous coordinates of endpoints. Oops, and this should not be P3. That should be a type. That should be Pm minus 1. And this should not be, yes, for n equals 4 super Yang-Mills theory, we're interested in 4 comma n, but more generally, you could imagine being interested in G m comma n. So you have an n by m matrix that contains the homogeneous coordinates of n points in Pm minus 1. Okay. Next, you have a matrix C that's k by n. And in principle, a priori, all three of these integers are independent. I'll discuss relations later, but for now, K, N, and M are completely independent. We're going to let this matrix parameterize, and I'll review this in a second, some M times K dimensional cell of the totally non-negative Grassmannian. And I just remind you, this is the subset of the Grassmannian where all Plücker coordinates are non-negative. So some of them are allowed to be 0. Okay, so to briefly review work of Postnikov, to begin with, I want to review I'm going to distinguish between two different classes of parameterizations that we're interested in. The first class is what we call Plabic parameterizations. And this is based on the correspondence between d-dimensional cells of the totally non-negative Grassmannian and planar bicolored or Plabic graphs with d+1 faces and n boundary vertices. So here I've drawn an example of a Plabic graph associated to a 6-dimensional cell of the non-negative Grassmannian G2, 6. And I won't review the construction in detail because it will be discussed in the discussion session, and many of you already are familiar with this, but we associate a face variable to each of the faces. You can also do this with edge variables. They're related to each other in a similar way to how cluster A variables and cluster X type variables are related to each other. For this application, I personally prefer the face variables because they're slightly more canonical. The only relation they satisfy, they're not all independent, but the product of all of them must equal to 1. That's why if you have d+1 faces, you only have d independent variables, so you're parameterizing a d-dimensional cell. Okay, from the diagram, one can read off a k by n matrix that parameterizes the associated cell as long as the face variables range over all positive real numbers. And again, this will be reviewed in the discussion. Now, we're also going to make use of non-Plabic parameterizations. This will also be discussed in the discussion. So how this works is very simple. We just recall that the dual to a Plabic graph, so here I've tried to draw the dual of the example I showed above. The faces are replaced by vertices being these dots, and the edges are replaced by these crossed edges. The dual to a Plabic graph is a quiver of either the GKN cluster algebra or a subalgebra thereof. The external faces here correspond to frozen nodes of the quiver, so I've drawn them in red, and the internal faces, in this case there's only one, are the mutable nodes. Okay, now mutating on a node with valence 4, like in this example, corresponds in the Plabic graph picture to carrying out a square move, like this. But at the level of the cluster algebra, I haven't drawn an example with valence higher than 4, but it's easy to do so. And in terms of the dual quiver, you're perfectly free to mutate on a node of arbitrary valence, in which case the face variables transform according to the usual transformation rule for X-type cluster variables, given by this formula where B is the adjacency matrix of the quiver and Fk is the node you're mutating on. However, when you do this on a node of valence greater than 4, it doesn't have any it doesn't correspond to any move at the level of the Plabic graph. It would try to take you to a non-planar Plabic graph. So it's still a perfectly fine cluster parameterization of your cell. It's just not one that corresponds to a Plabic graph. So therefore we call it a non-Plabic parameterization. So that just explains the vocabulary I'm using for these parameterizations. All right, so finally we come to the point. If you let C parameterize an MK dimensional cell of this totally non-negative Grassmannian, and then you look at this set of matrix equations, well, this is M by N, this is this is K by N, this is N by M. So the total number of equations you have here is M times K. And because you've chosen a cell that has dimension MK, that's what we instruct you to do as part of this construction. you have MK equations for MK independent phase variables. And so generically, for generic Z, you'll have isolated solutions. For the simplest parameterizations, you'll have a unique solution, but for more complicated parameterizations, you can have higher integer number of solutions that give you algebraic functions. Now, observationally, the solution often sets these phase variables to symbol letters of endpoint amplitudes. So by way of example, I chose an example that does not overlap with the ones that my collaborators have prepared for the discussion. This is a really simple example. Here's a playback graph corresponding to the top cell of the totally non-negative Grassmannian G26. And if you work out the solution for CZ equals 0 for some random matrix, a generic matrix, 4x6 matrix Z, here's what the phase variables work out to. And you see that indeed, the minus signs are rather interesting because we're talking, I mean, I understand them well, but I won't explain them. Okay, but the interesting thing is that you get these Plücker coordinates here, which are the cluster variables of G46, and also the symbol letters of 6 particle amplitudes. Now, in this case, I mean, you know, in this case, you might think it's kind of trivial that just the steps of solving this equation manifestly will give you Plücker coordinates. And for G46, you have the accident that Plücker coordinates are cluster variables. So this example by itself maybe is not terribly compelling. But if you start looking at more complicated examples, some of which you'll see in the discussion, it becomes rather compelling. So in particular, the first place where we were excited enough about this to decide to write a paper about it was when we found that precisely the 18 algebraic symbol letters that are known to appear in 8 particle amplitude. So if you remember from my chart of data many slides ago, the number 18 appeared. You can reproduce precisely these 18 algebraic symbol letters by solving the matrix equation CZ equals 0 for a certain 8-dimensional cell of the totally non-negative Grassmannian G2, 8. And Anders Schreiber will go through the details of this in his discussion. Now, full disclosure here, once you know that this is true, and once you know that, here I'm bringing in a lot of physics that the physicists know very well, but the following sentences will be obscure to some people. The matrix equations CZ equals 0 appear when you calculate Yangian invariants that we know from the work of Drummond and Farrow can be written as Grassmannian integrals of the form delta function CZ over product of cyclic minors. And when you carry out this integral, well, the first thing you do is solve CZ equals 0, which produces these things. And then you evaluate those minors in the denominator on your solution. So all of these factors we're encountering end up appearing in the denominators of Yangian invariants, which is a topic that's extensively studied for various other closely related reasons. But okay, once you know that this appears, you can actually go back to 2012 and observe that the 18 algebraic symbol letters are sitting right there in the literature. Okay, so here's the Yangian invariant associated to the cell we're interested in of G2, 8. It's a product of this thing psi, which is algebraic. So it has an algebraic denominator that has 1 square root factor in it. And then you've got these 2 5 brackets. And each of these 5 brackets has 5 denominators, one of which is just a Plücker coordinate like 1, 2, 3, 4, or 5, 6, 7, 8. But the other 4 of which are algebraic. So you get 1 + 4 + 4 = 9 algebraic letters, and those are precisely 9 of the 18 that fall into a single cyclic class. The other 9 come from the other cyclic class. Anyway, so they're there in the literature, but only realized long after the fact. Okay, so let me summarize this approach, or approach is maybe really even too strong a word, this observation about the connection between symbol letters and CZ = 0. We also found, as did Song-Ki and Lee, that sometimes if C is not a top cell, the solution, even in cases where it's rational, that means even in cases where the solution is isolated, can involve quantities that are not cluster variables. Here's an example. If you solve the equation CZ = 0 for this graph, here's what the solutions look like. And you see in here the quantity 1 × 4, 2 × 3, 5 × 6. The notation here is that each of these is a 3-vector homogeneous coordinate on P2, and cross is just the usual cross product. And this is the determinant of 3 3-vectors. This is not a cluster variable because the ordering is wrong. It would be a cluster variable if these things could be put in a cyclic order. So we know that this sometimes happens. We don't yet have a full theory or explanation to know, more precisely when this happens, how this happens, what kinds of things appear. Is it always the case that the things you get are permutations of cluster variables, as this one is, right? If you allowed yourself to permute these back into the correct order, this would be a cluster variable. So there are many open questions we have about this approach. We do know, however, that if C is a top cell, then you only encounter cluster variables. And in fact, by considering an arbitrary non-Playback cluster parameterization, you can realize all cluster variables this way. And essentially, this owes itself to the fact that there's the duality between GKN and Gn minus k comma n. But still, it would be good to more systematically understand what's going on. And I didn't. Oh my goodness, I didn't put the final conclusion of our most recent paper. We know how to extract or reproduce all of the currently known n = 9 symbol letters, including the algebraic ones, by looking at certain cells for n = 9. Okay.
Sorry, can I ask here?
Yeah, I've been going too fast. My speed has discouraged people from asking questions. So please go ahead.
No, I just wanted to ask, so you reproduce all letters, but does it mean that like any analysis that you do produces a letter, or sometimes it doesn't? Sometimes it's kind of a false result. So it's a subset of all results which are correct, or yeah, how does it work?
So, okay, so there are many. So if you allow yourself to consider arbitrary cluster parameterizations that are non-Playback, then there are infinitely many of them for G49. Okay, there are infinitely many cluster parameterizations, so you can get any cluster variable you want out of it. So from that point of view, it's not surprising that you can reproduce all the rational letters that are known, because those are cluster variables and you can get any cluster variable you want. What is maybe slightly non-trivial is that we have identified a finite list, a specific finite list of cluster parameterizations, specific mutation sequences from the initial quiver, such that if you solve CZ = 0 for those parameterizations and only those, you get the symbol letters and only the symbol letters, the 531 that are actually known to appear. So you don't get any other symbol letters, right? So if you look at the whole universe of infinitely many Playback parameterizations, you can get anything you want. but we've identified a finite subset that have the 531 letters and only those letters. So that, I'm shrugging because does it mean something? I don't know. I'm just the astrologer here, remember?
So then the question is, what is special about this finite subset?
Yes, exactly, right. And then regarding the algebraic letters, we also reproduce all of the algebraic, the 99 algebraic letters that are known from Songhe and collaborators. But in addition, we also produce a few additional algebraic letters that are not on their list. And there are at least three possibilities for what's going on. One is maybe there's some other parameterization we didn't look at that gives the algebraic cluster symbol letters and only the correct ones. Option number two is because those parameterizations are associated to non-top cells, maybe it's inevitable that they're polluted by stuff you don't want, like in this example. Or option three, maybe the algebraic letters we encountered that are not on Songhe's list will appear in the 17 loop 9-point amplitudes that haven't been computed yet. So all of these issues really highlight this point here, that it would be good to more systematically understand what's going on. Okay, thanks. Are there more questions at this point?
Yeah, can you say again, maybe you said already, those, the non-cluster guys, are they non-positive?
Yeah, like this one, for example.
Yeah, that one can
Yeah.
go to 0 even for a convex. Yeah, okay.
That's
Yeah,
right. It's obvious positive with respect to a permuted order.
Right, exactly. Right.
But yeah, it's definitely non-positive.
And so if instead you just you went back to the kind of stuff you guys were doing before, just looking at the poles in the form rather than the face variables.
Right.
In that case, of course, you're not going to see, well, you don't see these guys, but if
They
you do
always
that,
collapse.
you also don't see all of the algebraic letters. I guess you only see the ones in the usual format box and not any of the other ones. Is that right?
You don't. No. No. I think in this case you see all of them. But the worst problem there is you don't even see all the rational letters. So this was a point we didn't write it in our first.
No, sorry, I knew about n equals 8. I was asking about n equals 9, or about NMHV.
Okay.
Like, yeah. So let's say even for n equals 8, but for NMHV, I thought that I mean we get things other than the Formax box stuff that you get from. Oh, sorry. I guess it depends. All right. It depends which one of those. Sorry. If you look at those n squared MHV R invariants, can I just ask do you get all the letters that are seen just as poles of that R invariant or not?
For n equals 9, you're asking?
For n equals 8, even.
No, for n equals 8, I think you get all the algebraic poles.
You get all the algebraic poles. I see. You get all,
yeah.
so all the algebraic poles are sitting there in the n squared MHV singularity.
Yeah.
Okay.
But the problem is you're missing, even for n equals 7 already, you're missing rational ones.
You're missing rational ones. That's very funny. I see. So that's
very funny.
Yeah. So
you get one cyclic class of the non-clippers, but not the other one.
Yeah. Okay. Bizarre. Right. So that's the attention, because you might say the fact that you see these funny guys here is just telling you look at something more directly physical as well as sort of mathematically reasonable, that what reflects the boundary structure of the but somehow if you do that, you don't get quite enough.
Yeah,
And then
not
if you look
quite
at
enough.
the face variables, you get
Yes.
many more, but you get
But
a
too much.
few of these little crappy things. That very few of them. But yeah, I see.
Where is? Okay, this comment that I've just written will make no sense to people who view the slides online, and will only make sense to those who saw the talk. Yeah. So if you just look at the poles of Yangian invariance, you don't see enough. But if you look at all face variables, you see too much.
Okay.
Sorry, Mark, but you said if you look at top cell, then you don't see too much, right?
Oh, sorry. I'm sorry. I'm sorry. Yes, if you look at top cell,
Only cluster variables appear.
that's right. But then you'll never get the algebraic letters.
Right. Okay. That's yeah.
Yeah.
Right.
The top cell always has intersection number 1.
Right.
You'll
sure.
yeah.
Okay.
Okay, great. So
Mark, can I ask a
yeah,
question?
go ahead.
Sorry,
Oh, hi, James.
Hey, Mark. So you made a statement, I think you were making a statement a little while ago about the rational part of the alphabet. And I just wanted to see if I understood. Did you have let's see, a way to classify diagrams which allows you to solve these equations and get letters, which produces exactly the rational part of the alphabet showing up in the 2-loop NMHV?
We don't have, I think you use the word mechanism or algorithm, and that's giving us too much credit. We identified a set of quivers with the property that if you solve CZ equals 0 for the parameterizations associated to those quivers, you get exactly the 531 n equals 9 rational symbol letters and no more. But as to why it's those 9, no, we don't have it. Those. What is the theory behind why it's those quivers and not other quivers? No, we don't have.
I see. So you wouldn't, based on that, you wouldn't say maybe that exhausts the rational alphabet and you shouldn't expect more at higher loops or something like that.
Yeah, I don't feel confident saying that, because maybe you have to add a few more quivers. But yeah, it's I don't know.
Okay, thanks. Yeah.
Okay, great. Well, with all the questions, I have 3 minutes left for part 2. The good news is that I prepared this assuming that I would be low on time. So, this is a recent paper we wrote with Anastasia and our new student Li Cheng Ren, who came well trained to us. And I'm going to very briefly describe the apparent connection between certain polytopes one can associate to GKN and symbol letters. Now, the polytopes I'm going to talk about are dual to fans one can naturally associate to the tropical positive Grassmannian, generalizing a construction of Spire and Williams from 2003. And for the purpose of my talk, I'm going to take these polytopes as given. I'm not going to review how to construct them, either by taking Minkowski sums of Newton polytopes or by solving tropicalized Flicker relations. We're just going to take, and the biggest polytopes we analyzed were fully computed by these people, and we're just going to take that as a given. But in order to set the stage, let me give you an example of what I mean by associating symbol data to polytopes. So here's a polytope we've actually seen before. This is the pentagon I showed you regarding the parameterization of the 2,5 positive Grassmannian. And it has 5 facets. I've drawn here the normal rays. And so in my definition, the generator of a ray is always going to be the first integer point along the outward pointing normal, okay? So here are the generators of these rays. Now, in this particular example, if someone hands you this polytope and you know something about cluster algebras and you see these normal rays, you say, oh, I recognize those. these are precisely the G vectors associated to the G3, 5 cluster algebra. So I can say, I can naturally associate a cluster variable to every facet, because I say, okay, who's the cluster variable with G vector 1, 0? I'll put that cluster variable here, etc. But before I proceed too far, it's important that this isn't, if I just phrased it like that, it would seem like we're just playing a combinatorial game. And to some extent we are, but these are not, the polytopes we're going to be talking about are not some random, totally auxiliary polytopes that live in a universe that has nothing to do with anything else. They're literally polytopes associated to compactifications of G4, n, which is the kinematic domain of n equals Fourier-Ingles theory, the space on which scattering amplitudes are functions of, and the boundaries represent the boundaries of that space on which, and amplitudes have singularities on those boundaries. Anyway, this fact continues also for all of the polytopes. Well, there aren't too many choices, but the polytopes one can naturally associate to G4, 6, and 7, that the generators of the facets are precisely the G vectors of the corresponding algebra. For n greater than 7, the polytopes that one can naturally associate to G4n have two important properties. They manifestly have finitely many facets, whereas the cluster algebra is infinite, and many, but not all of the generators are G vectors of the algebra. In addition, you have these exceptional rays. So these two facts make it smell like these polytopes could be relevant to symbol alphabets, since we see these kinds of, that you don't get all cluster variables in symbol alphabets, and you get things, algebraic things, that are not cluster variables. Now, various partially overlapping approaches have been studied in the literature. I strongly urge you to read these papers. All of these papers, there's a lot of overlap between these papers, but there are significant things that are done better in the papers on which I'm not a co-author. So please read all of these papers. This is from 1912. Then I guess we had a community breakdown for a year due to COVID, and then we have these two nice papers in 21. Okay. Right. So the approach in our most recent paper also closely overlaps with these, but we come to battle armed with technology that's relatively new to this subject, this literature, tensor diagrams and the Fomin-Polowski conjectures. An endpoint tensor diagram for SLK is a finite graph drawn inside a circle with n-marked points along its boundary satisfying these properties. All boundary vertices are colored black and can have arbitrary valence. Every internal vertex can be black or white, but must have valence k, and each edge must connect a black and a white vertex. So now I'm going to draw some of these diagrams, and very confusingly, oh my gosh, do they look like Playbit graphs? But these rules are not the rules of Playbit graphs. So Thomas has agreed in the discussion to say a little bit more about how these two types of diagrams are connected. Yeah, I have some examples. Here are some examples that I show you. Now, an important concept is that of the tensor invariant. To each diagram, one can associate an invariant in the following way. Maybe I'll go ahead and show this example. You attach a momentum twister, a point in pk-1 to each boundary vertex. Then to every white vertex, you associate like an epsilon symbol with upstairs indices. To every black vertex, you associate an epsilon index with downstairs indices. And then you tie all the indices together according to how the edges in the diagram are. So for example, this rule that every internal vertex has index k is just this fact that they correspond to epsilon symbols. Now, this rule, this is a physicist rule because it's not precise. If k is even, there's an overall sign ambiguity because if you do a cyclic well, all the examples I've drawn are for k equals 3. But if k is even, there's a cyclic ambiguity. If you rotate one of these indices back to the front, you get a minus sign. I'm going to shove that under the carpet by saying that the correct sign is the one that evaluates to a positive number in the positive Grassmanni. So here are some examples of tensor diagrams and the corresponding invariants that you can read off from them. Now, these tensor invariants are the name invariant implies that there's a series of graphical moves that leave them unchanged. These are called the Skine relations, and here are some examples of Skine relations for SL3 and SL4. Now we come to the main point, which is the Fomin-Pilavsky conjectures. A web is a planar tensor diagram, and an arborizable web, from the French word for tree, is a web that can be turned into a tree diagram, no internal loops, using the Skine relations. Here it's important to note that the diagram doesn't have to stay planar while you're unfolding the loops. You have to have a planar diagram that can be turned into a tree, but that tree needn't be planar. So the Fomin-Pilavsky conjectures say that the set of cluster variables is the set of indecomposable. That just means you don't have two completely separated graphs sitting on top of each other, but uncorrelated with each other. Indecomposable arborizable web invariants. This has been proven by Chris Fraser for G39 and G48. Now, the cases G310, G49 that we apply it to are qualitatively worse than G39, G48. So I don't know what the mathematicians' current betting odds are on the correctness of these conjectures, but we've applied it to these cases and do not encounter any inconsistencies. And we've compared the results of our analysis with an independent check by Nicholas Tenke and Yorgos Papathanasiou and found no contradictions. So maybe the FP conjectures remain true. Maybe the calculations, the applications we need just don't push far enough to reach the first counterexamples if they're false, but we did not encounter a problem. So our strategy, using the kinematic functions that you can associate to these polytopes using the ABHY construction, we associate a facet to each facet of these polytopes a web. Now I'm highlighting this sentence because I think I've never given a talk before in which a single sentence has done as much work. So this sentence is over half the paper and is like a year of Li Cheng's effort. But I'm already over time, so read the paper. Now, if the web is arborizable, then by the FP conjectures, its invariant that you can read off from the diagram is a cluster variable. So in that way, to certain facets of the polytopes, we associate cluster variables. This will be the case precisely when the generator of the facet is a G vector of that cluster algebra. Next, let's look at webs that are not arborizable, but not arbitrarily bad. So we say that a web is almost arborizable if you can reduce it not completely to a tree, but you can eliminate all but one internal loop. So these are like one loop webs. To each such web, we assign a formal power series where the first non-trivial term W1 is the web invariant of that web. And the higher invariants are constructed by a certain braid operation that Li Cheng will describe in the discussion. In pictures, you have a web with a single inner loop. you take two copies of it, put them on top of each other inside the same circle. You take the two inner loops, and by a braid operation, I know the word braid has a specific meaning in the cluster algebra community. Here I literally just mean you take the loops, you cut them open, and you reattach them, braided in such a way, and you get a second invariant. That's W2. If you take M copies of the graph and braid them together, you get WM. Then you can read off the web invariant from that series, and we prove to all orders that the generating function has this form, where A is the web invariant of the original one loop web that you started with, and B is a quantity that you can read off graphically from this web. Now, you've seen these A and B before when I talked about the square roots of 4-mass box type. And we recall that A was a quantity that's positive value, in fact, over positive in the positive Grassmannian, and B was some other quantity. In the example I showed before, it was the product of 4 cyclic Plückers, 1, 2, 3, 4, 3, 4, 5, 6, 5, 6, 7, 8, 1, 2, 7, 8. What we find with these webs is that there's a graphical interpretation for what this B, who this B is, what its role in life is, and where it comes from. You can read it off graphically from these webs. And you can prove that this is the generating series to all orders. Now, following the suggestion made in this paper, we look at the poles of this function, okay, which are exactly of this type. I already mentioned this 4 is critical. And in all cases we've encountered, including the several hundred different, I don't remember the specific number, the several hundred, 300 something almost arborizable webs that we looked at for n equals 9, the poles are, oops, there's my eraser, the poles are always positive valued inside the positive domain. And this was related to a conjecture made in ALS, this paper, but there we used a different basis for invariance. We believe that there's a natural web series one can associate to more complicated webs, but we don't yet know the form of it. It was conjectured in this paper that you're always going to get a rational function. It's possible you start getting rational functions of higher order with higher order polynomials in the denominator. We certainly expect those for sufficiently high n. We don't know that they don't appear for n equals 9. So there's just a question mark regarding these. Okay, so to summarize this paper, using web series and invariance, we recover all previously known results about n less than or equal to 8, and find that candidate G49 polytopes do encode all currently known rational symbol letters and square roots of, but I emphasize, we do not, from this algorithm, as I've explained it here, precisely reproduce the algebraic symbol letters. We only identify the square roots appearing in them. If you want to identify precisely the symbol letters, you have to look at the other papers that I referenced a few slides ago. Here are examples of SL4 web diagrams that correspond to symbol letters of actually known amplitudes. So is there a pattern here? Why some web diagrams appear as symbol letters and others don't? We don't know. This is a data that we're sifting through. Okay, so I'm well over time now. I'll just end with, there are many open questions, several of which I've already mentioned. What ties together these various approaches having to do with playbit graphs and web diagrams? I hope to learn some of that from Thomas later today. So to summarize my talk, we see hints of possible positive geometries that have some features suggestive of being related to multi-loop amplitudes in n equals 4 super-Yang Mills theory, but they're still very far from understood. So I'll stop there. Thank you very much.